Oh, I didn't start recording this meeting. See, you will not remind me also, sir, why are we not recording the meeting? So, 4a upon L R into 2a into 2 upon L. Yes or no?
Yes, sir.
L
Yes,
upon
sir.
2 at the denominator becomes multiplied by 2 upon L. So ultimately 4a upon L is R into 4a upon L. So I will check. So now this 4a, don't cancel like this and say R is equal to 0. Apply your brains. This is denominator goes and becomes numerator. So 4a upon L as it is into L upon 4a is equal to R. L and L cancels, 4a cancels, R becomes 1 ohms. The resistance become 1 ohms. The resistance of new wire is 1 ohm. Do you see this? Yes or no?
Sir.
Yes, sir.
Sir.
So this is what I always tell, that no need to see what they have done. We can go by our own understanding. Length is given, area is given, resistance is given, we can always find the resistivity. Using the resistivity, length and area, we can again find the resistance. Resistance and resistivity, two different concepts. Yes or no?
Yes, sir.
Yes or no?
Yes. Yes, sir.
And these
Yes, sir.
questions will always come in the exam. That what happens when the resistance is doubled, area is doubled, area is half. Now you should know this. What happens when the length is doubled or when the area is doubled, when it is half, 2 times, 3 times, all these things. Questions. Number 1. On what factors does the resistance of a conductor depend? How many factors?
4 factors.
Four factors. Four
Which
factors.
Length,
Length,
area,
area, nature, and temperature.
nature of material, and
Temperature
temperature.
and temperature.
very good. Now read this question. Huh? Will current flow more easily through a thick wire or thin wire of the same material when connected? Why? What? Arya, I have told you this.
Thick wire.
Thick wire will be
Thick
more.
wire.
Through thick wire, more current.
It will
Why?
flow easily. Because area is more.
Area is
Yes,
more.
because cross section area is
Current
Area
is
is more.
directly
Simple
proportional to
language, what
area.
I had explained you. Wait. In simple language, how I had explained it to you the other day. In the simple language, just a minute. Huh? Just a minute. I had explained you that if there is a thicker wire, electrons can flow easily. Thinner wire, electrons can flow, not flow easily. So obviously, a thicker wire will have more conductivity, and that's what we had also seen, that resistance is inversely proportional with area. Yes or no?
Yes, sir.
Yes, sir.
Yes.
Yes, sir.
Write down the answer somewhere. Write down the answer somewhere. I I know that you know the answer, but still I want it in a scientific language. We will try to put it in scientific language. And again, they're speaking about a same material. So we know that resistance and resistivity are the characteristics properties of the given material. So for the same material, uh, for the same material, wait, no, okay, we also know that resistance is inversely proportional to the area. Thicker wire will have greater cross-section area, hence lower resistance, thus more flow of current. Therefore, thicker wire will allow more flow of current. The thicker wire will allow more flow of current. Yes or no?
Yes, sir.
Yes, sir.
Let me go to the next question. Let the resistance of an electrical component remain constant while the potential difference across the two ends decreases to half. So what will happen to the current?
It will also decrease to half.
It will decrease to half.
Why?
Because potential difference and current are directly
Directly
proportional
proportional
and
to each
resistance is constant.
Very good. Very, very good answer. So write down. Write down the answers somewhere, all of you. We know that just a minute. This is my answer number 3. We know that for a given circuit, if resistance remains constant, according to whom?
Ohm's law.
Yeah.
According to the Ohm's law, potential difference is directly proportional to the current. Therefore, if the potential difference is decreased to half, then the current will also decrease to half its value. So we have, then I have. Remember all these things. Finished? Wire coils of electric toasters and electric irons made up of an alloy rather than a pure metal. We have already discussed. Have we discussed why to use an alloy?
Yes.
Yes, sir. Yes,
Yes,
sir.
2 and 3 points we have discussed. Alloys have higher resistivity, high melting points. They do not burn. They do not oxidize easily. Yes or no?
Yes, sir.
Yes, sir.
Yes, sir.
Using the table, which among iron and mercury is a better conductor? So let me go back to my table.
Iron.
So tell me, who is a better conductor, iron or mercury?
Iron.
Why is iron a better conductor than mercury?
Because it has less resistivity.
Very good. The resistivity is less, and less resistivity means more conduction. And who
Yes,
is the
sir.
best conductor?
Silver.
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 I told you. But why can't we use silver?
Because silver
It,
is
Because it
costly.
It
is
has
less
low
sensitive
melting point.
and
Silver
less
is
resistive.
costly, and yes, it is costly. And then copper and aluminium. Next two best conductors are copper and aluminium. But we will use copper in the household equipments because again copper is costly. Aluminium is comparatively cheaper. We'll be using on the electric lines outside. Now, do you know one more thing? You know those windmills are there, na? Big windmills. You've seen those big windmills.
Yes, sir.
Yes, sir.
Yes, sir.
These big windmills, at times, you will find that the windmill is erected, but it is not operating. You know why? Because these windmills are connected with copper windings. Here there is a copper winding. Okay. And the people, you know what? They rob this copper. Copper ते इथलं चोरतात आणि विकतात. आणि कॉपर इथलं कॉपरच चोरल्यामुळे विंडमिलच बंद पडते. Do you understand? People do these kind of things also. So that is why they have to keep a watchman. But that watchman, what he will do, bichara man? How much he will pay attention? He also gets bored because these windmills are on the top of mountains and hills. So first of all, you don't get people to work as watchmen over here. And then those who know the value of copper, they go and do all these things. So if you at all you are planning to have a windmill, first check how to stop the robbery of the copper and then erect a windmill. Yes or no?
yes,
Yes.
We will discuss the very important point, resistance of a system of resistors. So when I'm going to connect 2 or 3 or more resistances, either in series or in parallel. Now I have already discussed this part once. Very quickly I will read all these things and then we will discuss what happens in the series connection, what happens in the parallel connection. Very important point, very interesting point. In the preceding sections, we have learned about some simple electric circuits. We have noticed how the current through a conductor depends upon its resistance and the potential difference. Current is always directly proportional to potential difference. So as the potential difference increases, current increases. It is inversely proportional to the resistance. As the resistance increases, the current decreases. In various electrical gadgets, we often use resistors in various combinations. We now therefore intend to see how Ohm's law can be applied to combination of resistors. If I am combining them either in series or in parallel, what will happen? And why do we combine that? That also we'll see at the end of the discussion of this topic. Why to connect them in series? Why to connect them in parallel? What are the advantages and all those things? There are two methods of joining the resistors. So the figure 12.6 shows an electric circuit in which the resistances R1, R2 and R3 are joined end to end. Underline this, joined end to end. Here, hence the resistances are said to be connected in series. Means you see, this is what a series connection, end to end. End of first resistor is connected to starting point of second. End of second with the starting point of third, means end to end. They make a chain. So this is called as resistors in series. You already know that. Whereas the figure shows a combination of resistors in which three resistors are connected together between common points X and Y. Right here, common points. They should have written the word common over here. काय फरक पडला असता एक word add केला असता. So yeah, where are X and Y? A and B actually it is. Common points X and Y, na? A and B. So point A is a starting point of R1, also starting point of R2, also starting point of R3. So R1, R2, R3 are parallel across A, and all three are having the same ending point B. So when I say parallel, I will say across. Parallel means what? Across. And series means what? End to end. ठीक है?
Yes, sir.
Now, resistance in series. What happens to the value of current when a number of resistors are connected in series in a circuit? What would be their equivalent resistance? Let us understand the activity. Now you see what activity we are going to do. Okay, I will just take a new and see, those donkeys were absent now for the second session. I just feel so irritated that I am discussing an important point and the donkeys will remain at home. Fine. See what activity we are going to do. Suppose if this is our circuit, one resistance, second, third, connected in series. I want to connect the ammeter. Where should I connect the ammeter?
Anyway.
In series anywhere.
In series anywhere. Anywhere I can connect the ammeter. So this was the positive terminal, this was the negative. Positive comes and connects with the positive of ammeter. Okay. So this was R1, R2, and R3. You know what happened? I connected all these things. The key was open. Key was not closed. Ammeter was placed over here. Do you understand?
Yes, sir.
Yes.
Now current started flowing from and now listen, understand the activity very carefully, all of you. This is very important. I plugged in the key. The current started flowing from here. What did the current do? Go from R1? Yes or no?
Yes. Yes,
It
sir.
passed through this, came outside, entered R2, passed through R2, came outside, entered R3, passed through R3, came outside, went into the ammeter, came outside. So ammeter is showing me what? Total current of the circuit passing through all of them. Yes or no?
Yes, sir.
Yes.
Sir.
My ammeter showed me 4 amperes as the reading. Okay.
Yes, sir.
Now what I'm going to do, I will remove the ammeter from here. I want to check what happens and I will put the ammeter over here. In series only, but here. Now ammeter is showing me which current, you tell me. the current which has come out only from R1.
R1.
Yes or no?
Yes. Yes, sir.
R2 and R3 are not there only. So that I will write as A1. मला काय वाटलं R1, R2, R3 मधून पास होऊन एवढी मेहनत करून करंट बाहेर आलाय म्हणून फक्त 4 अँपिअर होता. फक्त R1 मधनं बाहेर आल्यावरती करंट थोडा जास्त पाहिजे है की नाही, बिकॉज R2 आणि R3 मधून अजून करंट गेलेलाच नाहीये. येस ऑर नो?
Yes, sir.
Sir.
But surprisingly again it showed me 4 ampere. I was shocked. How did this happen? I said, let me do one thing. I removed the ammeter from here and I put the ammeter over here. Positive, negative. The key was opened actually. I will open first. What I'll do first, I will open the key. So circuit is disconnected. नाहीतर हात लावला तर मला shock बसेल. Then I will remove this ammeter from here and put the ammeter over here. And again I will now connect. And I'm interesting now की आता तरी करंट वाढला पाहिजे किंवा करंट झाला कमी झाला पाहिजे. But even after coming out from R1 and R2, current showed me the same value. You understand?
Yes, sir.
I felt, Areva, good. Let me remove this and put it over here. But then I realized whether I put it over here or whether I put it over here, one and the same, na? Because this is also after R1, R2, R3. This is also after R1, R2, R3, one and the same. Yes or no?
Yes, sir.
Yes, sir.
Every time the current was same. What is the conclusion that I draw from this? What is the conclusion, children? What is the conclusion?
Equal
In a
current
series
is passed
circuit,
through all circuits.
In a series circuit, the
in a
current will
series
remain
circuit,
constant.
when the resistances are connected in series, it does not make any difference to the current. Current remains the same. To each and every point, current remains the same. Yes or no? You connect it here, 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 anywhere you connect, it remains the same, it shows the same value. Correct, Aika?
Yes, sir.
Yes, sir.
So now I felt, let me see what happens to the potential difference. So first I connected it parallel across the whole circuit. R1, R2, R3, everything. You can see that this is first point is starting point of R1, the ending point of the combination. So I connected a volt across all three. So now what will this voltmeter show me? Whole potential difference of the entire circuit. Yes or no?
Yes,
Yes,
sir.
Yes, sir.
Yes, Bhakti, tell me. Bhakti?
Sir, by mistake.
Okay. So I found out that this volt was showing me 7 volts. I said, Areva, okay, fine. Then again my curiosity raised. I felt, let me now only connect through V1, that is through R1. So I removed the wire from here and I connected only across R1. And just as current remains same, I thought voltage should also remain same, but voltage decreased drastically and I got only 1.5. So now I was very happy. Ha, chala, voltage three badalte. Let me now check what happens if I connect voltage across two resistances. I got a little bit other value, say 2.5 volts, when these two were connected together. Or, sorry, I connected only second. It showed altogether different value. Means V1 across the first resistance was 1.5, but voltage across the second was totally different value. The voltage here was 2.5. And finally, I connected the voltmeter over here. It showed me another value, different value as 3 volts. So voltage across the third circuit was 3 volts. And when I connected the whole, all three together, it showed me 7. Do you understand this now part now?
Yes, sir.
Yes,
Yes,
sir.
sir.
I was surprised and current is remaining same, voltage all 4 times different values. V1 showed different, V2 showed different, V3 showed different, total V also showed different. But then I checked 1 plus 1.5 plus 2.5, how much?
4,
4 plus 3, how much?
7.
7.
7.
And did I get this 7? Did I get this 7?
Yes, sir.
Yes, sir.
Yes, sir.
So can I conclude V is equal to V1 plus V2 plus V3? Is it happening like this?
Yes, sir.
Yes,
Yes,
sir.
When
sir.
is this happening? When is this happening? In the case of series circuit. Yes or no?
Yes, sir.
So I find out two conclusions. When the resistances are connected in series, current remains constant. Current does not change. Am I right?
Yes, sir.
Yes,
But
sir.
the total potential difference across the circuit is sum of individual potential differences. Yes or no?
Yes, sir.
And now I have got V is equal to V1 plus V2 plus V3. And what is V? Tell me, children, what is V? IR? Yes or no?
Yes.
Yes, sir. Yes, sir.
Total current of circuit, total resistance of circuit. What will be V1? I1 into R1.
I1 into R1.
I1 into R1. V2 will be I2 into R2. Yes or no?
Yes, sir.
Yes, sir.
Yes.
And V3 will be for this I3 into R3. Yes or no?
Yes, sir.
But what I have seen, I1, I2, I3, I, all are same. Means all are I. So can I write now? IR is equal to I R1 plus I R2 plus I3, because I1, I2, I3 all are equal to I. Yes or no?
Yes,
Yes, sir.
sir.
So IR is equal to, can I
Yes,
take
sir.
out I common from all three?
Yes, sir.
What remains? R1
Yes,
plus
sir.
R2 plus R3. And I here and I here gets cancelled. R is equal to R1 plus R2 plus R3. This is my equivalent resistance of the circuit. So now I understand that when a circuit is connected in series, the equivalent R is equal to R1 plus R2 plus R3. Am I right? So the total resistance of the circuit is what? Resistance 1 plus
Yes, sir.
resistance 2 plus resistance 3. Sum of all the resistances is the equivalent resistance of the whole circuit. Yes or no?
Yes,
Yes,
sir.
sir.
Yes or no?
Yes, sir.
This derivation we will write tomorrow, but what do we understand? Total R becomes R1 plus R2 plus R3. Yes or no?
Yes, sir.
Yes, sir.
Yes, sir.
And on the other hand, when suppose if I had another combination wherein Shreya, okay, you can keep the mobile a little bit away from you. I understand what you're saying. Okay, this last point we will continue tomorrow only. But see, when the R1, R2, and R3 were connected in parallel. I did the same activity. I will check I1, I2, I3. Again check V1, V2, V3 and total. Means what? Total V will be like this. V1 will be only connecting over here. V2 only connecting over here. V3 only connecting over here. Are you understanding? Voltmeter I will
Yes, sir.
connect individually and
Yes,
totally.
sir.
Yes, sir.
Similarly, once I will connect ammeter over here. So it will show me only current through the R1. Remove from here, connect here. Show only current through the R2. Remove from here, show here. And finally remove from here and show here. This time, my voltage every time was same. Say 12, 12, 12 and 12. But current changed. One, then sometimes it was 2.2. Here it was 3.8. But total current was 7. So in parallel, what happened? Voltage remained the same, current changed, but the total of this current was the same. 3 plus 2, 5, 5 plus 1, 6, 6 plus 1, 7. So I became I1 plus I2 plus I3 in parallel. Whereas in series, V became V1 plus V2 plus V3. Are we understanding?
Yes, sir.
Yes, sir.
Yes, sir.
What do we know? V is equal to IR. V is equal to IR. So V upon R is equal to I. So V upon R. And voltage is every time same. So again I will write V upon R1, V upon R2, and V upon R3. V is common as a numerator. Remains 1 upon R1, 1 upon R2, 1 upon R3. V and V gets cancelled. Finally, I get 1 upon R is 1 upon R1 plus 1 upon R2 plus 1 upon R3 for a parallel combination. Yes or no?
Yes, sir.
Yes, sir.
For series, R is equal to R1 plus R2 plus R3. But for parallel, 1 upon R is equal to 1 upon R1 plus 1 upon R2 plus 1 upon R3. Yes or no?
Yes, sir.
Yes.
In series, current remains same. Voltage, total voltage was sum of individual voltages. In parallel, total voltage remained the same, but total current was sum of all the currents. Okay.
Yes, sir.
Yes, sir.
This is an important point. We'll stop over here. Tomorrow we'll continue. So goodbye, all of you.
Bye.
Bye,
Bye,
sir.
sir.
Bye, sir.
Bye, sir.
Right, sir.
Bye.